Assalamualaikum and good afternoon. Today we will discuss about chapter number 3. So the title is Quasi-Steady Flow. So quasi-steady flows in which the rate of change of mass flow is continuous with time, but the fluid acceleration and the forces responsibility for acceleration are negligible. In such cases, the steady flow equation may be applied with reasonable accuracy. And the example of this one is the continuous filling or emptying of the reservoir and tanks. So we will learn about the quasi-steady flow. Okay, so what is quasi-steady flow? Previously in Fluid Mechanics 1 and Fluid Mechanics 2, we only focus calculation on steady flow. Okay, steady flow means the, the flow rate is not changes. So means that along the time. So at any time, the flow rate is constant. But for quasi-steady flow here, so it means that the flow rate is become lower and lower, slower and slower, or the flow rate is become higher and higher. So means that you must calculate very carefully along the time. So the common example of quasi-steady flow is the flow from a constant tank like this. So mean, for example, we have a tank here, and then this tank is connected with a pipe like this, but okay, we don't put any inlet pipe at here. So means that the water that comes out from this pipe is actually depend on this water level only. So as you know, when water level become lower and lower, the velocity here will decrease, will become slower and slower. So means that if the velocity here is slower and slower, so the cross-sectional area of this pipe is constant. So means that the flow rate will become lower and lower. So this is the typical example of quasi-steady flow. Okay, so actually, if you really understand how to evaluate this one, okay, you may use the idea of Bernoulli equation to solve this problem. Okay, let's say we try to solve this problem first by using the Bernoulli equation. Okay, normally, I think you could imagine that if we have a different flow rate at different time, so we will use the idea of integration. So we integral the equation and then we get the answer. Yes, we will do that one. But before we do that, okay, so I will show you how to solve this problem by using the basic idea of Bernoulli equation. Okay, let's say we have this situation. We have a circular tank with a diameter of 1.0 meter here. And then the water level is 3 meter in the tank. And then it's connected with a pipe here. So, and then the height from the tank bottom to this one is 2 meter. So, and then the pipe properties is given in the slide. So we have F is equal 0.1. So I hope you still remember the meaning of F. F is the friction coefficient. So we take the value of F from the Moody chart. Okay, however, so normally in this question, I will give you the value of F. So means that you no need to calculate the value of F from the Moody chart. So and then the L here is 5 meter and the 9 meter is 3 centimeter. Okay, so the flow, as I explained previously, so because we don't have any water input here, so the velocity here is totally depend on the water level. So when the water level become decrease, so the velocity here is also decreased. Okay, then we try to calculate the Bernoulli equation by the idea of Bernoulli equation. So first, we take two reference point. One for sure here, the inlet, and the other one is the outlet. It's point number 2 here. So we know that the atmospheric pressure is act on both point here. So we have PATM here, and then the height here is 3 plus 2. So we could write the Bernoulli equation as this one. So and then we have we could cancel out the value of pressure, and then at point number 1 we could say that the velocity is equal to 0, and then at point number 2 here the height or the elevation is equal to 0. So and then we have Z1 is equal to 5 meters. So we have velocity at point number 2, because in this situation velocity at point number 2 cannot equal to 0 because the water flow at certain velocity. So and then we calculate the major losses. The major loss, so I hope you could do some revision for fluid mechanics too. So this is the equation for the major loss. So we substitute everything, so we could calculate the velocity at point number 2, means the velocity that comes out from this pipe is 2.356 meter per second. Okay, so however, when you do this, please bear in mind, please understand that this velocity is actually the maximum velocity could flow in the pipe. Why? Because this velocity, 2.356 meter, is only occur when the water level is 5 meter from point number 2 here. And then if the flow start, if the fluid start flowing here, so the water level will decrease, and for sure the velocity will decrease. Okay, so means that this is the idea of the discalculation. So and then, okay, let's say we know the volume of water inside the tank. So we could calculate by the idea of we have a circular tank. So we could calculate the area of the circular, and then we multiply with the height of the tank. So we could calculate like this one, and then the volume is 2.3565 meter cube. So and then we could calculate the flow rate that flow inside the pipe. So we know that the flow rate is Q is equal to A times V. So we have the A here. So the A here is the cross-sectional area of the pipe. So we have pipe property here. So we could calculate the cross-sectional area here, and then we multiply with the velocity. So we could get the flow rate. So and then we could imagine that if the total water inside the tank is 2.3565 meter cube, and then the flow rate is constant because the velocity here is constant. If the velocity is constant at 1.6656 times 10 to the power of minus 3 meter cube per second, so means that we could calculate the time the time to empty the tank. So we could calculate by having this equation, volume divided by the flow rate. So we could have 1414.8 seconds. So this is the way we predict for the first time what is the time to empty the tank. Okay, so this is the time, 1414.8 seconds. Okay, as I said, the velocity here is the maximum velocity because the velocity will reduce, will become slower and slower. So what happens if we take at point number 3? So means that first we calculate at point number 1, and then the velocity will become slower and slower, and then we try to calculate what is the slowest velocity in the system. So means that we try to make a Bernoulli equation between point number 3 and point number 2 here. So if we do Bernoulli equation, we compare point number 3 and point number 2. So we still have the equation, Bernoulli equation like this. So the height of point Z3 here is 2 meter. So and then we calculate the major loss here, and then we could calculate that the velocity that comes out when the water level come to this level is 1.49 meter per second. So and then from this velocity, we could calculate the new flow rate. So it is around 1.053 times 10 to the power of minus 3 meter cube per second. So and then we could calculate the time to emptying the tank. So it is around 2237.9 seconds. Okay, so what is this time? So this time is actually the longest time to empty the tank. So means that by doing this calculation, so what conclusion that we have? So we could say that because the water flow inside that pipe is become slower and slower, so means that the time to emptying the tank is actually become longer and longer. Okay, so but at least you must know that so the time to empty the tank must between 1400 and 2200 seconds. So means that it must be in between. So why? Because this time is our calculation based on the maximum velocity. And this time is calculated based on the minimum velocity. So means that if your prediction is not between this number or this time, means your prediction is wrong. Okay, that's number one. And number two, we go for the next step. So means that because you are final year student, you will become an engineer. So maybe you could make some conclusion. So what conclusion that you could make is, okay, let's say, for instance, for the simple calculation, you could take the average time. So you just take the average one, might be it is around 1800 seconds. So this is the average time between 1400 and 2200 seconds. So this prediction is maybe correct for this situation because you just average the highest velocity and the lowest velocity. You take the middle point. So and then you could you just make assumption that the velocity is constant all the time, and then you could say that okay, it is around 1800 seconds to empty the tank. Okay, that is the second idea. So mean first you could make a prediction what is the maximum level and what is the minimum level, and the second one you could make a judgment by having the average. Okay, that is the simple idea to calculate this one. Okay, so and then we go to the third way to evaluate this situation. Okay, so we know that water comes out from this pipe is depends on the water level from this tank. So instead of we just calculate point 1 and point 3 here, means the maximum and minimum point here. So why not we make a little bit precise calculation by dividing this tank into a small portion. So because the height is 3 meter, so might be it is suitable for us to calculate the to divide this tank into 10 constant volume or 10 equal volume for this tank. So and then after we divide into 10 equal volume, so we just point the center point at each point at each volume here. So for example, here, so the height is become 4.85. So here is 4.55 and this is 4.25. So the distance here is 3 meter divided by 10. So the height is 0.3 meter. Okay, so and then what we could do is we repeat the calculation, the first calculation that I show you. So we compare the Bernoulli equation for this point and this point. And then we could get the velocity of this one. And then from that velocity, we could calculate the flow rate inside the pipe. And then from that velocity, we could calculate the time to empty only this portion of water. So and then we repeat the calculation again for the second volume here, and then we repeat for the third volume and so on. So until we could calculate the last portion of this tank. So and then after we get the data, okay, so this is the the way you could simplify your calculation. So that's why in mechanical engineering program here, we train you to have makmal 1, makmal 2 module and so on and so forth, because it's just to make sure that you know how to develop your own table from your own works. Okay, so let's say we could make a table like this. So we have a 10 constant volume there. So we have a 10 points here. And then the height is like this. So it starts from 4.85, 4.55, and so on. So because this is the center point for each small volume. So and then we could calculate the velocity here. So and then from this velocity, we could calculate the flow rate that flow out from the pipe, and then we could calculate the total the volume of water that being flow out. So means only the volume of this small portion. So and then so we could calculate the time to empty that certain portion. So if you do this, okay, if you do this, you will have some kind of table like this. So means that what you need to know is when the height is decreased, so the velocity will become lower and lower. So this is the way you self-check your calculation, because as an engineer later on, okay, you will take a lot of data after this, and then you need to make sure that you have method to self-check what you did. Okay, so and then if the velocity is reduced, so means that the flow rate also reduced. So you could see here the flow rate is reduced. So and then the velocity, the volume of water here is remain constant. Why? Because we divide the tank into 10 same volume of water. So means that the volume here is constant uh, for each space. So and then because the velocity is lower and lower, so means that the time to emptying the water is actually increased. So you could see it's increased from 143, and then it become 165, and then it's become 215. Okay, so this is what you get. So and then as an engineer, you should know what kind of data, what kind of process that you need to know to evaluate or to get your final answer. If you get this table, you will find that to know what is the total time to empty the tank is actually not looking at the last row here. So what you need to do is you need to sum all the value here. You need to add all this time, because this time is actually refers to 10 different slot in the tank. So if you add all of these time, you will get it is around 1732.69 seconds. So this is the total time for to emptying the tank. So means that our first prediction is quite correct. Okay, because our first prediction, if we just use the maximum and minimum velocity, so and then we average the value, so we could get that it is around 1800 seconds. Okay, so this is the way we use our common Bernoulli equation, but you need some expertise to develop your own table, and then you know how to get the final answer. Then, after you get the time from that table, another idea that you could do is you could draw a graph. So if you need to draw a graph here, you must very carefully, you need to choose the suitable parameters for x and y, because if not, you maybe draw a wrong graph and it will not give you the advantage of your calculation. Okay, for example, in this situation, we have the volume that flow out, the flow out volume, and also the time to empty certain portion of liquid of water. So here, what I do is, okay, I just add the volume of this one. So mean that this is the first volume. So and then this is the time. So and then when the second volume finish, so means you need to add these two amount. So and then the time is actually you need to add these two times. So after you do that, you could have this one. For example, it start from 0 and then the time is 0. So and then the volume of first slot is 0.23565. The second slot is 4.47 and so on until it reach the total volume, which is 2.3565. And then the time will increase, okay, by adding this time and so on, and then you will get this set of data. And then from this graph you could do this kind of graph. So means that, for example, you could have time in your x-axis and you have the volume that you flow out for the y-axis. So and then if you see very carefully, this curve is actually a little bit curved, not a straight line. Okay, so and then what is the advantage for you to having a graph like this? Because it could ease your calculation later on. So for example, if you manage to develop this kind of graph, so means that at any time you could have a lot of data. For example, if you open the valve, you flow the water only for 1000 seconds. So you will find that it is only, okay, it's only emptying only 1.5 meter cube. So again, if you have another idea, for example, what is the time to flow only 1 meter cube of water? So means that you could start from here, 1 meter cube, you go here, and then you could predict that the time is maybe around this time. So means maybe it is around 660 seconds. Okay, that's why if you work in SAJ later on, you will find that there is a lot of chart developed by previous engineer to help you to calculate or to predict the flow in the pipe network. Okay, so the idea is, please make sure that you really understand to calculate, and then you could ease your work by having tables and draw a graph. Okay, so please do not depend on the calculation, on the integral calculation, because in integral calculation, you will only have one answer for one question. So if your supervisor or your superior asks you to check for another time or another volume, so means that you need to do the integration again. Okay, that is the secret why in some workplace you will find there is a lot of graph, because that graph will is actually the work from the previous engineers that could help you to solve problems. Okay, now I would like to show you how to use the idea of integration to solve these problems. Okay, first, again, I hope you could imagine. So we have a tank here. So we have a water from flow from point number 1 and point number 2 here. So and then we could develop a Bernoulli equation. So this is the Bernoulli equation. So and then the trick is, we know that the height here is h. So and then we fulfill the velocity here, okay, without substitute the value of z1. Okay, the pressure is 0. So and then the velocity at point number 1, it start from 0. So we take as a 0. So and then the value of z at point number 2 is also 0. But, okay, please do not substitute any amount for z1. Why? Because the value of z1 is changing. So it starts from 5 meter, but it keep reducing, it keep decrease. So means that the value of z1 here is not a fixed value. So you just substitute the value of z1 as h. It reflects the height of the water level here. So and then we substitute everything. So and then in this equation, you will find that we have two unknown parameters. One is h and another one is the velocity. So means that if the h change, so the velocity also change. So if you do this, you will have this term, and finally you could simplify the velocity at point number 2, means the velocity at the outlet here is equal to 1.054 square root h. So it is okay to have this equation. Why? Because in integration method, you need equation. You need equation. So means this is an equation. So means that we could do the integration by using this equation. So and then, because we have two unknown parameter, which is v here and also the h. So means that we need to develop another equation to help us to solve this problem. So we could use the idea of continuity equation, because we know that the water is incompressible. So mean the volume that comes in must be equal to the volume that comes out from the system. So I think from fluid mechanics 1, you know to calculate the continuity equation. So we have A1 V1 is equal to A2 V2. Okay, so we go for the A2 V2 first, because this is quite simple. So we have a tank here, and then we have a pipe here. So at point number 2 here, we could calculate the flow rate by calculate the cross-sectional area here. So this is A2, and then the velocity inside that pipe is V2. So we have this term. Okay, however, for point number 1 here, maybe we have a little bit difficulty, because it's not looks like a pipe. It's actually a tank. Okay, but we could get some imagination like this. Okay, so if the water flows continuously, so the water level here will decrease from this level to this level. So means that because the cross-sectional of this tank is circular, so it can be any cross-sectional area. It can be rectangular, square, triangle, and so on. Okay, so but in this problem, we have a circular tank. So, and then the water surface is actually in circular. So, and then if the water running here, so this water level will become like this. It will flow until this level. So means that we could say that the water level is actually moved from this point to this point. So, and then we could say that the cross-sectional area A1 can be taken like this. So we have a pi d1 square over 4, and the velocity can be determined as the time the water level moved from this point to this point. So because this height is h, so we could write the velocity is dh dt. Means that the time for h to change from this point to this point. Okay, so means that the idea of velocity here so can be written as dh dt. So v1 here is equal to dh dt. Okay, that is the trick to solve the problems. So and then what we need to do is we fulfill all the parameter that we have. So here, for instance, we could cancel out the value of pi and 4 because it will cancel each other. So and then we only have diameter 1 and diameter 2. So and then we could substitute the value of V2 here with the equation that we get here. Okay, so and then I think you already know how to solve problem in boundary layer in fluid mechanics too. The idea is simple. We bring the dt to the right hand side and then we bring the h to the left hand side because we have dh here. So we could write as h to the power of negative 1 over 2 dh is equal to 9.486 times 10 to the power of negative 4 dt. So, and then if we have two differential form like this one, so we could solve by integrating both sides. So we integrate left and right side. So for the left hand side here, so we could get this term 2h to the power of 1 over 2, and then the limit is h1 and h2. So and then for the right side here, because there are no terms of t, so we just add 1 terms of t. So and then for the limit of integration here, okay, so we put it is equal to h2 is equal to 5 and h1 is equal to 2. Why? Because we have a tank here. So this is our point number 1 and this is our point number 2. So the height here is 3 and the height here is 2. Okay, so from the Bernoulli equation, so we must look from this point to this point. So this is 5, so and then this is 2. So means that for our integration, okay, we need to put the limit of 5 and 2 for the integration. So please do not take 0 to 3 because the water level here is not 3 meter. The water level here is actually 5 meter from the datum or 5 meter from the point number 2. So it starts from 5 meters and then it ends at height of 2. That's why we take these limits in our calculation. Okay, please make sure that you really know to take the correct limit for your integration method. So and then we substitute the limit here 5 and 2 and then we get it is around 1732 seconds. So if you see the answer that we get here, it is close to the our previous calculation 1732689. So we have here 173276 seconds.